Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from an Introduction to Mechanics by Klepner and Kolenko. We will continue to discuss topics from Chapter 6, Angular Momentum and Fixed Axis Rotation. In the last class, we have seen the general motion of a rigid body, which can be decomposed into two components. One is the translation of the center of mass. Second, the rotation around the center of mass. So consequently, all our equations have two components. One is the spin component and second one is the orbital component. In today's class, let's see how to derive the work energy theorem for such a general motion. In the previous module, we have derived work energy theorem for a particle where we have seen that the total work done in moving the particle from initial point A to final point B, WBA, is nothing but the change in kinetic energy between these 2 points, KB minus KA, where WBA is defined as an integral equation, integral RA to RB F dot dr. So we have taken the equation of motion and did an integration with respect to position, and that's how we have derived this equation. Now we can generalize this for a rigid body and show that work energy theorem divides into two parts, one dealing with the translational energy and the other one dealing with the rotational energy. First, let's look into the translation part. So this is the translation of the center of mass. So the equation of motion of the center of mass, we know F is equal to md square r by dt square, or in terms of velocity v, this is m into dv by dt. Then what's the work done when the center of mass is displaced by an infinitesimal amount dr? We know that velocity v is dr by dt, so I can write dr equal to v dt. So work done is nothing but force multiplied by the displacement, or dot product of force vector and displacement vector. This is F dot dr. F is mdv by dt, dot dr is v dt. And this term I can write as derivative of half mv square, because derivative of v square is 2v dv. So 2 and half cancel and you have this term. Okay. And what about the total work done when you move from initial position A, denoted by position vector RA, to final position B, denoted by position vector RB. So this is integral RA to RB F dot dr, and when you take the derivative of the right hand side, you already have a differential, so differential and integral cancel, and when you apply the limits, this is going to be half mvb square minus half mva square, where vb is the velocity of the center of mass at the final position, va is the velocity of center of mass at the initial position. So when you compare this with the work energy theorem for a particle, they look almost the same. Just that here the equation is written in terms of the center of mass. Okay. Moving on to the rotational part. So equation of motion for fixed axis rotation about the center of mass. We know in the case of translation motion, it is F equal to ma. Since we are talking about pure rotation, just replace the linear parameters with the corresponding angular parameters. So instead of force, you have torque tau. Instead of mass, you have moment of inertia I. Instead of linear acceleration, you have angular acceleration alpha. Okay. Since we are talking with respect to center of mass, you add a subscript 0 here. So tau 0 equal to I0 alpha. And alpha is nothing but rate of change of angular velocity omega. So this is I naught d omega by dt. Now what's the work done for an infinitesimal angular displacement d theta? Now angular velocity omega is d theta by dt. So I can write d theta equal to omega dt. Now work done for this displacement is tau naught into d theta, which is I0 d omega by dt multiplied by omega dt. On the right hand side, I can write as derivative of half I naught omega square. Now if you want to calculate the total work done from position A to position B, so theta A is the orientation at position A, theta B is the orientation with respect to center of mass at position B. So the total work done is integral theta A to theta B tau naught d theta, and on the right hand side once again the integral differential cancel. Applying the limits, I get half I naught omega B square minus half I naught omega square. So first one is the rotational kinetic energy at the final position, second one is the rotational kinetic energy at the initial position. So once again I find that the integral equation corresponds to the change in kinetic energy. So when I combine these two parts, I can write the general work energy theorem for a rigid body as WBA, the total work done in moving from position A to B, equal to KB minus KA, where the kinetic energy K has two components, one corresponding to the translational motion of the center of mass, half mv square, two corresponding to the rotational mass around the center of mass, half I naught omega square. So the general form of the work energy equation remains the same in all the cases. Now let's use this information to solve some physical problems. If you recollect the problem of a drum rolling down a plane in the previous class, so we have found an equation for the acceleration in the previous class. In today's class, using energy method, let's derive an equation for the velocity. So the problem goes like this. Consider a uniform drum of radius b, mass m, and moment of inertia I naught equal to mv square by 2 on a plane which is inclined at an angle beta. If the drum starts from rest and rolls without slipping, find the velocity v of its center of mass after it has descended a height h. Okay. So consider this is the initial position which is at rest, and after some time it has descended a height h, so this is the new position. So going by the previous equation, this is position A and this is position B. And if this angle is beta, from geometry you can see this angle is going to be beta. Let L be the horizontal length traversed by this drum corresponding to a descendance of h. So L is the horizontal length, h is the height, this angle is beta, so sine beta equal to h by L. Okay. And what are the various forces acting on the drum? Of course, there is weight which is always acting vertically downwards. And since this is rolling on a surface, you have a normal force N which is going to act vertically upwards with respect to the plane. And there is always frictional force acting against the translation motion. And from the geometry, if this angle is beta, this angle is also going to be beta. So you can resolve weight W into two components, one perpendicular component and one parallel component. Okay. And the perpendicular component of the weight is going to act vertically downwards against the normal force. So these two cancel. So for the translational part, you need to consider only the horizontal component of the weight. Okay. Now assume that omega is the uniform angular velocity with respect to which the drum is rolling down, and capital V is the linear velocity or the translation velocity. Our aim is to find an expression for capital V. Now let's write down the energy equation for the translational motion. Integral A to B F dot dr equal to half mvb square minus half mva square. Let's calculate the right hand side first. VA is the velocity as the initial position. We know that the drum starts from rest, so velocity VA equal to 0. Vb is the final velocity, capital V, so right hand side is half mv square. Left hand side is the total work done. How do you calculate the total work done? Total force multiplied by total distance. So the total distance is L. What is the total force? You have horizontal component of weight acting towards the right, which is the positive direction. So if this angle is beta, horizontal component is W sine beta, then you have force F acting in the negative direction. So total force is W sine beta minus F multiplied it with the length L. So you get W sine beta minus F into L equal to half mv square. Moving over to energy equation for the rotational motion. Integral theta a to theta b tau d theta equal to half I naught omega b square minus half I naught omega a square. Once again, solve the right hand side first. Omega a is the angular velocity at position A, but at this position it is at rest, so omega a equal to 0. Omega b is the final angular velocity, which is nothing but omega, so right hand side is half I naught omega square. And the total work done is nothing but the total torque multiplied by total angular displacement. So let's say the total angular displacement is theta. And what is total torque? Torque is nothing but force multiplied by perpendicular distance. So force is F and the perpendicular distance is nothing but the radius of the drum, which is B. So the total torque is Fb multiplied by total angle theta. This is equal to half I naught omega square. We also have a constraint equation because the drum is rolling without slipping. So I can write the linear length L is nothing but the angular length beta multiplied by theta. So B theta equal to L. So this follows from the pure rotation. Okay. So we have all the required information. Now let's solve this equation. So in this equation, instead of b theta, I can write L. So I have FL equal to half I naught omega square. Now we know the relation between linear velocity and angular velocity. Angular velocity omega equal to linear velocity v divided by radius b. Okay. So I can write from the previous equation FL equal to half I naught into v square by b square. Now substitute for FL in the first equation. I can write sine beta equal to h by L. So W into h by L minus F is nothing but half I naught v square by LB square into L equal to half mv square. So this is the first equation in terms of equation 3. So L and L cancel, so I can write WH equal to half I naught v square by b square plus half mv square. The half term is constant, take it outside. Now you can make some more simplification. The v square term is also common. You can also take that outside the bracket. So you have half v square into I naught by b square plus m. I naught, the moment of inertia of the drum about its center of mass, is nothing but half mb square. So this is half into half mb square by b square plus m into v square. B square cancels, so I have half into m by 2 plus m into v square, which is 3 by 4 mv square. So weight W is nothing but mass m into g. So left hand side is mgh, which is equal to 3 by 4 mv square. From this I can get a simple expression for the velocity v equal to square root of 4gh by 3. Now if you want a general equation for any object rolling down the plane, so we know that half mb square is the moment of inertia specific for a drum, right? So instead of writing this specific equation, I can write the general equation for moment of inertia, I naught equal to mk square, where k is the radius of gyration. Okay. Now you can follow the same procedure. So instead of half mb square, you can write mk square and do the simplification. Then you get the general equation v equal to square root of 2gh divided by 1 plus a square plus b square. So this is true for any shape. Okay. Let's do a couple of quick problems related to rolling on an inclined plane. A spool of thread unrolls itself under the action of gravity. So calculate its acceleration. So as shown in the figure, a spool of thread, when you let it free, it's going to unroll, and you want to calculate its acceleration. So this is very similar to rolling down on an inclined plane. So we have done the derivation of acceleration of an object which is rolling down on a plane, and we have considered the specific case of a drum where the moment of inertia equal to half mb square, where b is the radius of the drum. So as I said, that is a very special case. So if you want to consider a general scenario, instead of using the specific equation of moment of inertia, you can give a general equation like mk square. So if you go back to the yesterday's derivation, so instead of I naught, you substitute mk square and follow the same procedure, you get a general expression for acceleration. So that's going to be a equal to g sine theta divided by 1 plus k square by b square. So we are going to start with this general equation. Now in our case, this angle is 90 degrees, sine 90 equal to 1. So acceleration a equal to g divided by 1 plus k square by b square. Now you can approximate this shape to a disk. So in the case of disk, we know moment of inertia I naught equal to half mb square. Okay. So mk square is half mb square. From this I can write k square by b square equal to half. So substitute for k square by b square here. So a equal to g divided by 1 plus half, which is 2 by 3 g. Let's do one more simple problem. Three bodies, a ring, a disc and a sphere having the same radii b are simultaneously dropped from the top of an inclined plane. Which will come down first? So whichever having the highest acceleration, that will come down first. Okay. And we know the general equation for acceleration, a equal to g sine theta divided by 1 plus k square by b square, where k is the radius of gyration of the shape. Let's take the case of ring first. In the case of ring, we know that moment of inertia equal to mb square. So mk square equal to mb square, from which I can write k square by b square equal to 1. So a equal to g sine theta divided by 1 plus 1, which is 0.5 g sine theta. Now in the case of disk, moment of inertia equal to half mb square. So I can write mk square equal to half mb square, from which k square by b square equal to half. Now substitute for in this equation, you get a equal to g sine theta divided by 1 plus half, which is 0.66 g sine theta. Moving over to sphere, where the moment of inertia about the center of mass is 2 by 5 mb square. So mk square equal to 2 by 5 mb square, from which I can write k square by b square equal to 2 over 5. Now substitute in this equation, I get a equal to g sine theta divided by 1 plus 2 by 5, which is 0.1 g sine theta. So compare the value. G sine theta is common, so you just compare the coefficient. You can find that acceleration of the sphere is higher than the acceleration of disk, which is higher than the acceleration of the ring. So the sphere is going to come down first, followed by a disk, finally the ring. So that's about topics from chapter 6. We will move on to chapter 7, which is about rigid body motion and conservation of angular momentum. If you look at the translation motion, to study translation motion or linear motion of any system, what we do is we will first choose a convenient coordinate system, then we will denote the position of the object by a vector r. So r is known as the position vector. So once you identify position vector, all other relevant parameters can be described in terms of the position vector. For example, if you are choosing a Cartesian coordinate system where the axes are x, y, z, you can write position vector r as xi cap plus yj cap plus zk cap, right? Once you define r, you can define velocity as dr by dt, acceleration as d square r by dA square. Then you can write down the equation of motion and solve it. Okay. So the position vector is the most fundamental parameter. The question is, can we define a similar vector to denote the angular orientation in the case of angular motion? So can we have coordinates theta x, theta y, theta z, which are rotations about x, y, z? Then using these three coordinates, can we specify the angular orientation as a vector? In other words, we are looking for a vector theta, which is theta x I cap plus theta y j cap plus theta z k cap. Is this possible? Unfortunately, this is not a possibility, and there is no way to construct a vector to represent an angular orientation. Why? I can illustrate this with an example. Suppose you have a rectangular object as shown here. So let's first calculate the vector theta x I cap plus theta y j cap, where theta x is counterclockwise rotation around the x-axis by 90 degree, and theta y is the counterclockwise rotation around y-axis by 90 degree. Okay. So theta x I cap plus theta y j cap. So here I first perform theta x, then theta y. So let's do that. So first rotate it by 90 degree in the counterclockwise direction around x-axis. So you get this geometry. Now you perform theta y. Rotate it around the y-axis in the counterclockwise direction by 90 degrees. So you get this particular orientation. This is theta x I cap plus theta y j cap. Now let me calculate theta y j cap plus theta x I cap. So here you perform theta y first, followed by theta x. So you rotate the object around the y-axis in the counterclockwise direction by 90 degree. You get this geometry. Now you rotate it around the x-axis counterclockwise by 90 degree. You get this particular orientation. So clearly you can see that these two orientations are completely different. Or in terms of vector notation, theta x I cap plus theta y j cap is not same as theta y j cap plus theta x I cap. But if you take the linear equivalent, you will find that x I cap plus y j cap is always same as y j cap plus x I cap. So this is a fundamental identity, a fundamental relation in the case of vectors. Vector addition is always commutative. Since x and y coordinates follow this principle, I can say that x, y, z, etc. are true vectors. On the other hand, theta x, theta y, theta z, etc. are not true vectors because their vector addition is not commutative. That's why it's not possible for me to write an angular vector similar to a position vector. So this is not a possibility. However, this is not the end of the story. Even though the angular position cannot be represented by a vector, the angular velocity, which is the rate of change of angular position, is a perfectly fine vector. So we can define angular velocity vector as omega equal to d theta x by dt I cap plus d theta y by dt j cap plus d theta z by dt k cap, which is omega x I cap plus omega y j cap plus omega z k cap. So the angular positions are angular position cannot be represented by a vector, but the angular velocity can be represented by a vector. And how this is possible? Even though rotation through finite angle do not commute, as we have shown in the previous example, when the rotations are very small or infinitesimal rotations, they do commute. So in the case of extremely small rotation, I can represent omega, which is limit delta t tends to 0, delta theta by delta t. I can represent this as a true vector. That's why angular velocity is a vector. Same way, angular momentum is also a vector which follows from the very definition of the angular momentum. We know angular momentum L is R cross P. It is defined as a cross product, and we know that cross product is applicable only in the case of a vector. So by the very definition, angular momentum is a vector. So both angular velocity and angular momentum are vectors. That's for today. In the next class, we will discuss about conservation of angular momentum. Stay tuned for that. Thank you.